The second problem in introset 5 says that you have a hole in the side of a container and water to a depth of 4 meters above that hole. And we want to analyze 7 grams of water as it flows out and figure out the exit velocity, the velocity with which that water will exit the cylinder using energy conservation. Now, people will use Bernoulli's equation to solve this and will say that, well, Bernoulli's equation is equivalent to energy conservation, or at least it embodies energy conservation in a certain situation that applies here, and that's good. I would not give full credit for that just using Bernoulli's equation. I'd probably give you 7 points out of 10, depending on the course, and say that, yeah, okay, that's good, but you didn't show energy conservation. You didn't really use energy conservation. You just waved your hands and said that Bernoulli's equation involves energy conservation. Well, I'll give you 10 full points if you use Bernoulli's equation and first show how Bernoulli's equation follows from energy conservation, which is really what we're talking about here. Now, at the time you first see problem number 2, you will not have seen Bernoulli's equation, or at least not in this course. So we really need to develop it from some other point, because really what we're doing here is building up to deriving Bernoulli's equation. Okay, well, and if you don't know what Bernoulli's equation is at this point, that's fine. That's expected at this point. Okay, so what do we want to say? We want to say, well, how does energy conservation apply here? Well, it applies this way. If a chunk of water, this blue chunk here, 7 grams of water is expelled here, then it's lost from this system, which means that the water level goes down a little bit. So effectively, that 7 grams was kind of spread over the surface, or very near to the surface of the water. So we take 7 grams of water away from the surface and replace it with 7 grams of water here. What has happened to the energy of the system? Well, that 7 grams of water that's been lost here and replaced here represents a change in potential energy. The potential energy of the system has decreased. It's less than it was by the potential energy of 7 grams at this height. So we've lost 7 grams from here, replaced it here, we've lost potential energy. Now, to analyze that a little more in a little more detail, okay, we have 7 grams. Gravitational force on that 7 grams is 0.07 newtons. Now, what we're building up toward, of course, is a change in potential energy. In this course, the definition of potential energy change is that it's equal and opposite to the work done by a conservative force. This is a general definition. It unifies the idea of potential energy change, unlike a simple formula like mgh, which applies in certain circumstances, but in other circumstances it's 1/2 kx squared. In another, it's negative k q1 q2 over r. What formula you use for potential energy depends on the situation, and it depends on how much work conservative force, be it a gravitational, an elastic restoring force, an electrostatic force, a magnetic force, any conservative force does work on a mass or on an object. It changes the potential energy of the object by the rule I gave. So that's where we're approaching here. So we have a 7 grams mass of 7 grams. And let me clarify what the board says here. Mass 7 grams, period. The gravitational force on that 7 grams is about 0.07 newtons, which I assume anybody can calculate. It's 0.007 kilograms times approximately 10 meters per second squared. That'd be 0.069 something, but or 686, I believe. Okay, so there's your gravitational force, approximately 0.07 newtons. We're not going to split hairs over significant figures and so forth here. We're trying to get the idea. The work done by gravitation. I use delta W gravitation to indicate the work done on some interval. Okay, that's not really a change in work done. It is work done, but the delta indicates that we're doing this on an interval. Okay, that's going to be what? Well, if we take upward as a positive direction, and we have to calculate the work, we have to be aware of the directions of our displacement and the direction of our force. So if we take upward as a positive direction, then our 0.07 Newton gravitational force, the force by the conservative gravitational force, is negative 0.07 newtons. We multiply that by the displacement from here to here, which is negative 4 meters if upward is positive, giving us a positive 0.28 joule work. Now, whether you choose a coordinate system or not, the force is this way and the displacement is this way. They're in the same direction, so you end up with a positive work. If you took the downward direction to be positive, you'd have plus here and plus here and plus here. Okay, well, the change in potential energy then is equal and opposite to the work done by the conservative force, the gravitational force, and that's going to be negative 0.28 joules. So the potential energy changes by negative 0.28 joules. Okay, now what about kinetic energy? Because we have the work energy theorem that says that the work done by the net force is equal to the change in kinetic plus a change in potential energy. So we want to talk about the change in the kinetic energy. Well, the initial kinetic energy, which I designate by Ke sub 0, is 0. So that the change in kinetic energy is just the final kinetic energy. Change in kinetic energy is the final minus the initial. The initial is 0, so final minus initial is just equal to the final kinetic energy. And that's 1/2 mvf squared, where m is the mass. It's our our 7 grams, our 0.007 kilograms. Okay, now we want to apply the work energy theorem. It says the work done by the net force is, or work done by non-conservative forces, is equal to the sum of the changes in kinetic and potential energy. And I think I misstated that a minute ago. I think I said the work by the net force. Because the work done by the net force is equal to the change in kinetic energy. Work done by non-conservative forces is equal to the change in kinetic plus change in potential energies. So let's hope I didn't mislead you too badly there. Okay, change in kinetic plus change in potential energy then has to be 0, since non-conservative forces are assumed to be absent in this ideal case. So that our final kinetic energy, which is our change in kinetic energy, plus our change in potential energy is 0. Our final kinetic energy is therefore the negative of our change in potential energy. Just subtract change in potential energy from both sides if you wish. Final kinetic energy is 1/2 mvf squared, so that's equal to negative change in potential energy. We easily solve that. We easily solve that for the final velocity. We get final velocity is, now there's a plus or minus here when you solve for a square root, but we're really only interested in the speed. Still, I'll put the plus or minus in here. And you can choose plus or minus. It really depends on how you orient your coordinate system. It could be minus. Okay, so solving this for VF squared and then plugging in our potential energy change. Twice the potential energy change would be negative 0.56 newtons, because here's our potential energy change. And negative of that would be plus 0.56 joules. We divide that by the mass, 0.007 kilograms, and we do the units. Joule is a kilogram, meter squared per second squared. Dividing by the kilogram, we have then meter squared per second squared for the units up here, so that when we take the square root, we do get meters per second. And 0.007 goes into 0.56 about 80, well, it goes into it 80 times. The square root of 80 is between 8 and 9 and much closer to 9. It rounds off to 8.9. Now, if you use your 9.8 meters per second squared up here and do a little more precise calculation, that'll change this just a little bit, and you might end up with an 8.8, even an 8.7, but I don't think it would go that far. Okay, so that's how we think through this. We calculate the potential energy change of that 7 grams. we set that equal to the kinetic energy change, where we assume the kinetic energy at the surface, the velocity is 0. Down here, then we've got to have a velocity, so our kinetic energy change matches the negative of our potential energy change.